What I'd like to demonstrate in this film is the possible use of a downhole orbital vibrator as a fracture detection tool. To that end, we've designed an experiment which demonstrates a concept which may be very valuable as a downhole tool for locating fractures in the subsurface. The experimental equipment you see before me here consists of a Data 6000 signal analyzer, a DC voltage generator, an XY recording oscilloscope, two pieces of PVC tubing approximately 3.5 feet tall. This piece you can see it just has an end cap on the end. This is an identical piece except that we've attached some boards to this piece of pipe, and we've indicated the orientation of the boards by these arrows on top. The downhole orbital vibrator we'll use in this test was constructed in the lab here. It consists of an electric motor with an eccentric weight, a geophone housing in the upper half containing two orthogonal 40 Hertz geophones, and a couple of rabbit ears here with arrows on them to allow you to determine the orientation of the geophones when this device is lowered into these pipes. The pipes are filled with water, and we'll demonstrate that when an orbital source is in an isotropic non-fractured media, the motion of the source is circular. However, when this orbital source is lowered into a media containing vertical fractures, the motion of the source will become elliptical rather than circular. And it's this elliptical motion of this orbital vibrator that's our key, that will be the key to the presence of vertical fracturing. In addition, the orbital motion, the direction of the orbital motion can be utilized to determine the orientation of the vertical fractures. Let me demonstrate the downhole vibrator, first of all, before we put it into the pipes. I'm going to switch on the vibrator. I'm using a DC voltage here. Remembering that we have two orthogonal geophones in the vibrator, we should see two sinusoidal signals, approximately 150 Hertz, that display a 90-degree phase shift. We're going to display the two geophone outputs in trace format on the Data 6000 analyzer. You'll see both traces and you'll see their phase relationship. At the same time, we'll input the output from those geophones into this XY oscilloscope and look at the shape of those two signals in that format, which gives rise to a figure called a Lissajous figure. One input is input on the X direction, and the other input is input in the Y direction. This particular figure is very nice because for circular motion and a 90-degree phase shift between the two geophones, the figure will turn out to be circular. However, when the motion is, when the phase and amplitude correspond to elliptical motion, you'll notice that the figure generated in this XY oscilloscope becomes elliptical. These ellipses and circles thereby give us a sense of the movement of the downhole orbital source. Let me go ahead and turn on the source here first of all. You'll notice the torque immediately causes the vibrator to rotate. Over here on the XY oscilloscope, you'll see a circular Lissajous pattern indicative of two signals of more or less the same amplitude separated by a phase of 90 degrees. We can confirm the phase relationship and amplitude relationship of these two signals by switching over and taking a look now at the two output traces on the data 6000. Two sinusoidal signals, approximately the same amplitude and sampled at about a half a millisecond. You'll notice here that the phase between those two signals is approximately 90 degrees. The peak of one signal corresponds to the zero crossing of the other signal. So at least sitting in the air, this orbital vibrator operates in a manner consistent with our notions about orbital vibrators. What I'd like to do now is I'd like to take this vibrator and place it into this pipe which is full of water and show you that the motion of the vibrator remains orbital. Now you can see that as I lower this orbital source into this pipe, you'll see that the motion remains essentially orbital, continues to remain orbital, as indicated by the circular Lissajous. And also, if we look at the traces coming out of the data 6000, you can see that we still are maintaining this approximate 90-degree phase difference and geophone outputs with approximately equal amplitudes. Now, what would happen if I rotate this tool in the tube? You'll see that we remain more or less circular as we rotate the source within the tube. There are some hints of ellipticity here, probably due to the fact that the tube is not of uniform wall thickness. But for the most part, our response of our orbital source has remained circular in nature. Now, what I would like to do is I would like to take the source out of this pipe and lower it into the pipe in which we have glued to the sides of the pipe these wooden boards. Now, as as this thing gets lowered in there, you can see that we've generated now an elliptical Lissajous figure. Let me try to center this a little bit better. There we go. You'll notice here that one of the characteristics of Lissajous figures is the fact that for this particular display, whenever the major axis of the Lissajous figure is either east-west or north-south, the phase between the two geophone signals should be approximately 90 degrees. Let's go over to the data 6000 now for this Lissajous figure and see what the approximate phase relationship is between those two signals. Here on the data 6000, you can see that indeed we do have an approximate 90-degree phase difference between the two geophone signals. However, because of the amplitude variations, we're getting this elliptical Lissajous figure. Okay, let's go back now and let's rotate the source in the hole. And as we rotate the source in the hole, let's keep an eye on the Lissajous figure. Okay, here we go. We're rotating the source in the hole. You'll notice that the source rotation and the orientation of the Lissajous figure, the major axis of the Lissajous figure, are tracking each other. And that the major axis of the Lissajous figure whenever the Lissajous figure is north, south, or east, west, the geophones, as indicated by the yellow arrows, line up parallel and perpendicular to the boards which have been attached to the tube. Let's go through a 360-degree rotation again. Here we're 45 degrees. Parallel again. Whoop. 45 degrees. Back to parallel. So in a sense, the outputs from the geophone allow us to, one, determine the presence of fracturing by the shape of the Lissajous figure, and two, if it be possible to either rotate the source mathematically or physically, we should be able to determine the orientation of the fractures, assuming that our fractured wellbore has a direction of maximum rigidity and a direction of minimum rigidity. Now I'm going to go ahead and remove the source from the hole, and you'll notice that as we come out of this zone, how we go back to circular motion again on the orbital source. I'll shut this off now. That basically demonstrates the phenomenon that I wanted to show using this equipment of how you can possibly use a downhole orbital source as a fracture detection tool. Thank you very much.